Okay, so today's presentation, how do neural networks work, or how do neural networks learn? I'm going to kind of present a broad picture, or more differently, a microscopic picture of how do the hidden units that are the kind of building blocks of neural network work, and we're going to look at this through Bayesian inference, okay? Second. Oh. Okay, so if we start over with a very small problem that we typically solve with TAGI, so what we have here is kind of the function we're trying to learn, the relationship between some output y and the input x. So we're going to do this with a single hidden layer neural network, so it's a very simple network that we can write in this form, okay? This is nothing special, this is typical one hidden layer neural net, feedforward neural net. So we have inside here what are going to be our z layer. So x is the input, W is the input of weight represented by each of those arrows that multiply the entry x plus a vector of bias that adds on each of those hidden units. We're going to pass those z's into an activation function. In this case, we're considering ReLU. Okay, we pass this into ReLU, then goes here. We multiply each of those activation units by a weight. This is what we have here. Plus, we add one bias term here to get our z output. Z output, this is not directly what we measure. We measure z output plus some observation error that gives me y. Okay, this is the typical structure. Now, what happens if we have a set of here, say 20 observations, and I have some uncertainty. So at epoch 0, since I'm Bayesian, I'm going to define my prior knowledge for all the weights and bias. That's going to be reflected in the prior output for my network that is look like this, my prior expected value and confidence region. Then after one epoch, I haven't learned yet the whole function. Okay, I need to go over several epochs in order to learn the function. And I don't like that. I don't like the fact that we cannot learn this by seeing the data only once. We need to go over data over and over and over again. And this is a simple network, but we see the same thing with larger networks. So this is ResNet 18 with 11 million parameters applied to Cypher 10. We see the performance of TAGI compared to Backprop. It's roughly the same performance. We can go faster than them. So we can run over 50 epochs rather than 150, but yet 50 epochs is too many, okay? So if we look a little more closely at why do we need to learn over multiple epochs, it's because at the beginning, we have very weakly informative prior to define what is the mean vector for our parameters, weights and bias, as well as the covariance matrix, which represent what is the uncertainty around each of those parameter values. We're going to call this eta, or hyperparameters, so either the mean or covariance. And this is the issue, okay? So what do we do instead? We're going to learn over multiple epochs, where we define our prior hyperparameter eta 0. We're going to pass into TAGI, learn over a first epoch what are our abated hyperparameters. And we're going to feed that over and over again in a recursive way. And in that case, we're going to stop training using a kind of validation set, using an early stopping procedure. But I would really like to learn over a single epoch, not having to do that repeated process. Why is that? First is because we want to do online learning for all of our applications in structural health monitoring, what DAI is currently doing with TAGI LSTM. We need to go over and over the time series multiple times. We would like to be able to learn as data is collected, okay, to both learn online, but also to be able to, if we carry on and do interpretation over time, if things change, we want to be able to change our parameters or change what the neural net learn, okay, but right now we can't do that. And this is also connected to continual learning, okay? If we want to operate in changing conditions, we need to be able to learn sequentially, not learn over epoch. And what do I mean by continual learning? Imagine the same function we had previously. If we want to learn this in a continuous way, so I start to observe some of the points, then I start to observe other points, and I keep doing like this. So you see, I kind of observe the response of my function sequentially. I can't do this. I can't learn sequentially to do this. And in practice, for many of our SHM applications, where we want to learn behavior over time, we're in conditions that can change over time, we need to unlock that capacity to learn in a continuous fashion. meaning not only learn online, but learn in changing environment. Typical neural net, if you start learning here, just with these points, all the weights and bias are going to adapt to this one. Then you're going to move somewhere else. They're all going to adapt to there. And then you're going to forget what you learned for this one. And it's never going to perform well. Neural nets only work if you start seeing data from everywhere in your domain. Then another batch from everywhere, then another batch from everywhere. You can only see data that is randomly sampled across all your domain. Okay? This is only a 1D example, but this is true across the type of data or problem you would like to do with neural nets. And finally, why would we want to learn in a single epoch? Because we want the speed up that it could provide. So if we would run 1 epoch instead of 10 or 100, this is a 10x or 100x speed up from what we can do. Okay, so for all these reasons, I would really like to learn into a single epoch. The question, can we do it? Okay, so this is what I investigated, or these are the results, this is what I investigated to see what prevents us from learning from 1 epoch. And my strategy to do this is to flip the problem over. Okay, I didn't go with a 11 million parameter neural net to try to find what's going wrong. It's too complex. Okay, so I go with the simplest way possible and then build up. Okay, and I see at the beginning, I can learn in 1 epoch. Okay, I'm good. I want to see when I stop learning from 1 epoch. To try to pinpoint and put the finger on what is preventing us from learning from 1 epoch. To try to see, okay, is there a solution to that bottleneck? Okay, so we're going to start with linear regression, something very simple. Then we're going to go with a 1 hidden unit neural network, then a 2 hidden unit, and a 3 hidden unit neural network. And we're going to see when it stops. Okay, since we don't go more than 3 hidden units neural network, you can see that we're not going to go far. But this is going to still provide us insight about how is it working and why we see that behavior that we cannot learn easily in 1 epoch. So this is exactly what I just presented. So if we start with linear regression, okay? Let's imagine the setup where I represented with the DAG, the structure of a linear regression. We have only one input variable x, one output y, and we can model this problem just this way. So z, the intermediate variable, equal a times x plus b, where a and b would be my parameters, okay? And we can say that y equals z plus v, where v would be our observation error. Okay, this is simple as possible linear regression. Then we can say, let's treat the quantity we don't know, w and b, as random variable. Okay, and we know that if we consider them as Gaussian random variable, this as a closed form solution. Okay, and we assume now, just for sake of simplicity, that our observation error is 0 variance. So our observations are exact. So it's going to remove the observation process. That's going to make the whole thing simpler. So the question I want to ask you first is, how many data points do I need with respect to observations of x and y's? How many pairs of x and y's do I need if I want to learn with TAGI, the same Gaussian inference process that we use usually, if I want to learn the weight and bias, w and b, in 1 epoch? How many data points do I need to learn w and b? Exactly. I want uncertainty around them. I want to learn them exactly. One data point? Two? Do we have someone suggesting 2? Do want someone who wants to try something else?
This is a linear regression problem, right?
Linear. So imagine z equals wx plus b.
But what is the truth? The truth is also
The truth
assuming it's linear?
The truth is linear.
Okay.
Okay? There's a line somewhere.
Then 2.
I have how many points do I need on that
2
line?
points to 2 point, right?
2 points. It's only 2 points. Okay, so theoretically, if we see 2 points on that line, I should be able to infer instantly w and b. Okay, starting from any prior for these quantities here. Okay, do you think we're going to achieve that?
Achieve it in this context?
Yeah.
Yeah. Because we don't have uncertainty. Everything is almost deterministic. Yeah, not almost deterministic. So yeah.
Okay, so we expect it's going to work. Okay, let's try this. So theoretically, we only need 2. Okay, let's look at this. So before looking at this, we're going to look at many possible contexts where we can explore this problem with more and more simplification or more and more simplifying hypotheses along the way. So the first thing is going to be sequential inference with full covariance. Okay, we said that we have two observations. So we then gonna observe one observation, then the second one. Okay, this is why it's sequential. Then batch. Then we're gonna see the two observations at the same time with full covariance. Then we're gonna go sequential, but with diagonal covariance. We're gonna neglect the covariance between W and B, the weight and the bias. Then we're gonna do a batch inference with a diagonal covariance, so the same thing, both at the same time, but neglecting all the correlation whatsoever. What's gonna happen, okay? And we're gonna see where is it gonna break into this. And finally, we're gonna look at non-identifiable case. What if my function for my line is over-parameterized? We're gonna look into this when we're gonna get there. So first, let's review together the maths to do this, okay? It's fairly simple, but just to get it fresh in your mind, because we're gonna reuse this along the presentation. So we're going to look at it first for the sequential formulation. So we see one observation, then we see the second one. So we're going to say W is univariate Gaussian with mean mu W variance sigma W squared. B, the same thing with mu B sigma B squared. Okay, X is my input value. This is a real quantity. We have this linear form Z equals WX plus B. Okay, W is random, B is random, then Z must be random. I can express this same expression in a kind of vector format, okay? Except I express x tilde being x and 1, because 1 is the term for the bias. I multiply by the vector WB, I'm going to get exactly the same very simple formulation. I know, since W and B are Gaussian, that I can express my joint PDF for Z, W, and B as a multivariate normal, okay? No approximation, this is going to be exact. So here I can express all the quantities that are in here using mu Z is going to be equal to mu W times X plus B. This is equivalent if we express this in a vector form times my vector, that X is a deterministic vector, times my vector mu WB. So mu WB is not the product of W times B. Here's just a vector that contains the mean of W and the mean of B, okay? Then I can do the same thing, so linear operation for the variance sigma Z. The covariance between Z and W and B, a 2x1 vector, is going to be given by this operation. So again, it's a standard transformation, linear transformation of Gaussian random variable. Nothing new, nothing special. Then we can condition. If I observe Z, how can I infer the posterior for W and B? So in that case, it's also going to give me a Gaussian where these conditional mean and covariance are going to be given by the same expression, business as usual. All the quantities are already been identified here, and Z are each of my observation that I'll observe sequentially. Meaning that I'm going to observe a first observation Z, I'm going to obtain a posterior, I'm going to observe the second observation, obtain the second posterior. Okay, so it's a two-step inference process. That's why I call it the sequential. So let's look at our first case, okay? Sequential inference with full covariance. So we're going to consider a full covariance for W and B, no diagonal assumption, no simplification, okay? In a two-dimensional case, it's negligible cost. With TAGI, when we have a million parameters, this is really costly, but here we can easily afford it. So we have our prior for W and B. It's a very broad prior. So you see W and B. Sorry for the really small font. I'm not yet in full control of Python. I'm learning on the fly. I will eventually settle down in the better habits of having larger font. But this is W and B, my two parameters. These are my prior, okay? Mean plus and minus 1 sigma, okay? Mean 0, mean 0. The true values are the little crosses, okay? And if we use that prior into my linear model, Wx plus B, what we have here, it's going to look something like this. So my Z is here on the vertical axis. We have the mean for Z and the plus and minus 1 standard deviation. This is for X. Everything that runs across this presentation is always normalized between 0 and 1 to make it easy, okay? But it's generalized in any interval. It's just because I want to keep things simple. And the reality, the truth, is if we use those parameters that are represented by the little crosses, would be the dark line here, okay? So this is just my prior at epoch 0. I haven't seen anything. I'm going to see a first observation. We see that around that point, my prediction collapsed, and we can see that from the previous step to this one, we reduce the uncertainty about my parameters. Okay, not too bad. If I see the second point, if we're right, I should collapse exactly on the line. I see my second point, I collapse on the line, and my posterior for each of the parameters collapse on the parameters. Okay, in here, no approximation. I could have started from any prior, it goes straight on it, one epoch. Okay, so this is great, but this is a trivial problem. Okay, so then we're gonna look at the batch formulation. Okay, this is something that is very useful for us in neural network in order to take advantage of parallel processing. What's gonna happen if we try to do the batch formulation? So in this case, we're not gonna see one observation, then the other. We're gonna see both observations at the same time. So in that case, that setup was exactly the same, except that now x is a two-dimensional vector. Okay, so x is a vector, so z is gonna be an output vector. But we have only one w and b that are shared for both x's. Okay, so now I can still express this in a vector matrices form. I have two rows because I have two outputs. These two x's are constant, but w and b are still Gaussian random variables. Okay, so I can express now still this as a multivariate Gaussian, where now it's a four-dimensional output because I have z1, z2, each for x1, x2. Okay, then I have again the same mean vector covariance matrices where I can still, with the same linear operation of Gaussian random variable, express everything, where x now is a matrix of constants. Okay, x tilde, which is this model matrix that I have here. Okay, then I can condition on the same thing, but now keep in mind that this covariance matrix contains more term. Okay, this is a 2 by 2 now. It's not a 2 by 1 like before because I have a covariance for my two variables, w and b, for z1 and for z2, okay? But I can still condition and have still the exact same operation where the size of these increases a bit because I have now two observations, but other than this, it's business as usual, okay? So this is my prior, so same prior as I had before, same thing, true values are the same, this is my prior. So I'm gonna see my two observations at the same time. Is it gonna work, is it not gonna work?
I don't see why it wouldn't work.
Any insight?
I don't think it's gonna work as well as before. It will still be decent.
It's still be decent?
We don't have observation error, right?
No observation errors.
It should collapse as well in the true state.
Everyone agrees? Someone abstain?
Everyone abstains.
Okay, so good call. It works as well. Okay, one epoch, if we consider full covariance between everything, business as usual. Okay, one epoch, we learn everything there is to know. Case 3, now we start with simplification. Okay, we're going to consider that the covariance between our, it's sequential, it's not batch and war, we go back for sequential, so one observation then the other. But now we're not going to consider the covariance. Okay, we're only going to infer a diagonal posterior for w and b. Okay, other than this, same process. Okay, this is going to work, this is not going to work.
Yeah, it's not going to be the same.
It's going to be the same?
Yeah, in the sequential context, I think it will mess up things because after the first update, you will neglect some of the information, the cross covariance. So there are going to be some more uncertainty and a little bit of estimation.
Anyone? Insight?
Makes sense.
Make sense? Let's see. First observation. If someone wants to change their mind, or we go with the first?
I think it will work as same as before. I'll be the one to call it.
So, second observation? Yes, no, yes, no? Oh! So yeah, second observation started to mess up the thing because we neglected the covariance between our two cases. So we're still at epoch 1. Okay, we've seen our two observations once. What if I see again the same observation over multiple epochs? Am I going to reach the correct value or am I going to stay biased? Biased or correct value?
Correct value.
Zach, you seem to be on top of the leaderboard now.
Get me working. I think it will get better, but there will still be something off.
So let's see. So we go back to the first observation. Second, okay, we see the discrepancy reduce a bit, okay? And if we carry on, it gets better. So as we go and see more epochs, it goes to the true value. But now if we consider a diagonal covariance and neglect the dependency between W and B, we can't reach it in one epoch. Okay? So 5. So if we consider diagonal covariance structure here, so see if we consider diagonal covariance, if on a simple problem like this, we can infer in one epoch, 11 million parameter neural net is not going to do it either. Huh? We can imagine it. But let's see still, okay, what if we could manage the covariance? Is there other things that would prevent us from learning? Okay, because this is not the only approximation we're doing. This is just one of the things. We see one of the key elements to learn in one epoch is the covariance. Okay? Because doesn't mean that because we can do it here, we're going to do it neural net. But if we can do it here, we won't do it in neural net either. Okay? Because it's more advanced than this. So whenever doesn't work here, it's not going to work in the other one. But it's not because it works here that's going to work in the other one. But here we include covariance is something key. Then we're going to do something a little more funky. Okay? Batch inference with diagonal covariance structure. Okay? The batch here is a little different because what we're going to do if we do batch inference with full diagonal covariances is like a parallel sequential processing. What does it mean? Okay, look at my little snippet of code. Here I have 2 observations. Okay, so in this case I'm going to do it over a loop because I have only 2 instances, but in theory the advantage of doing this is that you would do parallel processing. So you would calculate the update step for all of your observation in parallel. So in case of TAGI, you would run say 500 nodes, which would all calculate update step in parallel. And then you would collect all the update step and apply them all together. Okay? But here, we neglect the covariance. So we neglect the effect that 2 observations could have effect on the update of each parameters. We do all of them independently. Okay? So in that case, we do this. We calculate independently the dm, ds, the change in the mean, the change in the covariance. We do this on 2 steps because we have only 2 observations, and then we're going to apply both together, okay? And here, if we want to do this, we need to clip the variance of the same thing as in TAGI. This is going to be the topic of another seminar coming soon, but we're doing the same thing in TAGI, okay? We realized before we were limited to very small batch sizes, okay? And the why is that? Is because we didn't consider this. When we consider the batch of multiple observations simultaneously, what happened is that observation 1 tell me I should have a big update for that parameter. Observation 2 tell me I also need a very big update for that parameter. And at the end, by how much it asks to shrink the variance shrinks so much that it shrinks beyond 0. That doesn't happen when you consider covariance. Because these 2 observations, since they're very similar, the network realized that these are the same observation. So you consider them as the same, and they're going to have a limited effect on shrinking your variance. But if you neglect the information coming from the dependency, you're going to have updates that are way too big, okay, for some parameter. And typically, you're going to get some negative covariance. Okay, so you need to shrink the update for covariances, otherwise you get negative covariance right away, even in such a tiny problem.
And one question, how do you decide 3? Because of the number of...
No, the rule of thumb. I just try whatever smallest value could work here.
Okay,
But
so for any data set size, always 3?
No, I mean, no. In this case, it's just for that 2 observation, very simple network. I have already derived some kind of rule of thumb rules that are more general for TAGI. They are way more complex than this. I'll present them in a complete seminar. But this is essential for neural nets as well, if you want to do batch processing, because you're going to have multiple updates that don't consider the redundancy of information that you can have in your batch, because all the updates are made independently of each other. Okay?
In batch size 1, there's no, like in the original implementation of TAGI, we don't restrict it.
We didn't restrict it, and that's why we were limited to 10 to 20 observation in a batch.
But for single and like for those cases, it still doesn't
No, because you do one update, then you're gonna have a value, then you're gonna say, given that this is my prior, how much should I change my prior from that new observation? So it's never gonna make one update from one observation that shrinks the variance more than the initial variance you add. This only happens when you take multiple observations at the same time, because then you're gonna have two update steps that didn't spoke with each other, and that both want to do a big correction on the value. And typically that will very soon get negative covariance, everything stops, like blue screen of death, you cannot do anything anymore, okay? So here, even with that small linear regression, I observe exactly the same behavior, the same pattern that appears. So now we have, again, same prior, the effect of that prior on my function. This is what I'm trying to learn. So now what are the expectations? Before Zach speaks, because he might know the answer. Anyone who wants, maybe I suspect he hacked in my presentation. Anyone has any guess? It's gonna work better, worse?
Bayesian first with diagonal, it's the same as before, right?
It's before we're considering a diagonal, but we were working sequentially. So we're seeing one observation, then the other. Now we're seeing the two observations at the same time, but without considering the dependency between those two observations.
Multiple epochs like before.
But worse or same?
A little bit more maybe like a couple more epochs, I would say.
Okay.
Worse than K3.
Worse than case 3?
I would.
Other guys?
More epochs.
More epochs?
No idea.
No idea?
Less epochs.
Less epochs? Ooh. So this is really going to discriminate now. We have a good case to shuffle the leaderboard. Okay? So, epoch 0. First epoch. Okay? Even the update at first epoch is really bad. Because both updates were made without considering what is the other information. So it's really off. It isn't ever going to learn. What if I do another epoch? Is it going to get on track, or it's never going to get there?
It's gonna get on track.
Gonna get on track. So epoch 1, not much better. 2, okay, now we start to see something's getting there, but it takes loads of epoch, okay? It's not that good, but we feel that we're getting there to the correct value, but we're epoch 19, epoch 20. Okay, this is a 2-parameter linear regression. Okay, we're far from our 11 million parameter ResNet 18. Okay? So in this case, it really hinders the capacity to learn if we consider batch. And this is something we observe with TAGI as well. So whenever we want to do very large batch size, say 1,000, we typically need more epochs to learn. Okay? Kind of same phenomena at another scale. Okay? But the exact same kind of symptoms that appear on the other scale. Okay, now we're gonna make it a little more complex. So now we're gonna have our diagram. So the relation between x and z has now 2 branches. I'm gonna over-parameterize my function. My real thing is still a line, but I'm gonna make the line a little harder. I'm gonna say z is gonna be equal to w1x plus w2x plus b. Okay, now I have 2 parameters, w1, w2. I have 3 parameters total. But I have 2 parameters that are a function of x. This is going to work.
And identifiability.
We have an identifiability because we don't know if it's w1, w2. Am I going to be able to learn this with 2 points?
It feels like there's many ways to get to the same spot,
And
which means it's possible to learn it. This equation is just not stable.
Okay, any other insights?
well, linear algebra is like whenever you have to have equal number of equations as unknowns. I mean, in this case, observations represent equations. So 2 equations, 3 unknowns.
No bueno?
Yeah, I don't know.
Any other insights?
But I think it will learn still.
And I play like if I would know these answers, but it's just because I run the test and I learned from those. But before running the test, I didn't do the right answer either, and that's why I did all this. to get some training data about how it really works. So don't feel like I'm treating you like these are easy answers. I didn't do the answers before running the test either.
It seems like it's gonna work, I don't know. It's gonna work, but technically it shouldn't, right? If we go by
Your reasoning is right. 3 unknowns, 2 parameter,
To observation.
3 unknowns, 2 observation? Something is weird.
But we're doing multiple epochs, that's the difference.
No, we want to do 1 epoch.
Oh, in one epoch it's not gonna learn, but in multiple, yeah, it's gonna
Okay,
learn.
but we still have the same objective. We always want to learn in 1 epoch.
Okay, no then.
So no? Anyone?
I think it learns, but with more info.
Zach, you're sure?
Yeah, I think you'll still get an answer. It's not stable.
So this is my product. Now I have W1, W2. B and W1 are the true values, but now those are over-specified. Okay? And the answer on my product is even broader because now I have 2 variables. Okay?
So W2, the true value should be 0.
I mean, there's no true value. There's no need of W2. So either I could say W1 is 0 and W2 is something, or it's unidentifiable. But only one of them would be sufficient to learn the system.
There's
Okay.
infinite solutions, right, basically.
There's theoretically infinite solution.
But there is a true value for W1. So
It's the value I use to generate the data.
okay. And when you generate it, W2 is set to be 0.
It's not, I use the same 2 data points as before. It's only that now the model has 1 extra parameter.
Okay.
Okay, 1 more degree in freedom, that is not at all necessary. But what if in real case my problem is over-specified? Is it still gonna learn? Okay? So 1 epoch, boom.
Wow.
Okay, but there's a caveat there. It learned exactly the function. So the relationship between x and z. But it didn't learn the parameter exactly. So you see the uncertainty on bias goes straight in. But the uncertainty on the parameter, W1 and W2, hasn't shrink. How is this possible?
But how come you didn't carry it? How come you don't have uncertainty on the prediction?
Exactly. What explains this?
They cancel each other?
Negative covariance. Okay, whenever you see these kinds of things, symptoms of negative covariance, and this is related to non-identifiability. Whenever you have 2 things that you don't know what they can be, one can be high, the other can be low. This is negative covariance between those 2, negative correlation. One is high, the other is low. So these 2, I only plot the marginal variance, but the covariance terms are highly negative. So if you look at these 2 terms in red, these are the covariances between this to 1. So negative and the same value as the variance. So it's perfectly negatively correlated. So what it means, when this one is high, this one is low. When this one is low, this high, this one is low. So at the end, when you sum them up with the negative covariance, it shrinks. Okay, so these 2 remains unidentifiable, but you can exactly learn the relationship between the input and output, even if you cannot pinpoint what exactly are those values. Okay? Then we're going to do same thing, but with diagonal covariance. Okay? We're now going to consider the dependency between our observations. What is going to be the results? So before, we have full covariance here. Now we're going to have diagonal covariance. Are we going to learn in 1 epoch?
No, I mean, always
No, from what we saw before, shouldn't work. Okay? So first observation, second, third. So we have kind of the same behavior as before, but still is going to get to the correct value despite neglecting the correlation. Okay? What if instead of having W1x plus W2x, we have 22 variable? Is it still going to work? In the same way?
Yes.
Yes? Yes, it's going to work. Okay, I tested. No matter how many variables you add, you get the same result. Okay, you can infer the input-output relationship exactly, but you remain to have lots of non-identifiability between your parameters. Perfect. So the conclusion from that first very simple linear regression experiment, so as long as you're going to consider the full covariances between the parameters and also between the outputs and the parameters, you're going to be able to infer the posterior in a single epoch. Okay, whether you're working in a batch mode or in a sequential mode. Overall, in terms of efficiency, sequential processing is more efficient than the batch processing. Why? Because that covariance matrix can grow really large. When two observation doesn't matter. When you have lots of observation, this is going to grow. When you go sequentially, it's much more efficient. Okay, this is an example why Kalman filter is so efficient, because you progress and you interpret time step after time step. If you would like to do a Kalman filter with all the times at the same time because you're a full covariance, that would be really expensive. Okay, this sequential processing, it's what makes Kalman filter so efficient. If we neglect the covariance in the for the prime, then sequential and batch processing will require multiple epochs. So as soon as we neglect the parameter covariance, parameter correlation, we're going to need multiple epochs. We can't get away without a single epoch. And whenever we neglect the covariance between sigma z and our parameter, in the case where we want to do a batch processing, in that case, we're going to require update clipping. So we cannot do full updates for our parameters, so the mean values in the covariance, because we're going to get negative covariance. And this is the exact same error we see as TAGI. And finally, if we have some not identifiability in our system, we can still learn in one epoch the input and output relationship, even if we cannot learn the parameter exactly. Okay, we're going to come back, we're going to reuse this result in the next ones. So first, if we look at a neural network that is building upon a ReLU activation function, the result of this, if we try to learn this function, is going to be a piecewise linear function, a little bit like this. Okay, this is not drawn. This is really, if we apply a neural net on this function, it would make piecewise segment, where each piecewise is the result of an interaction of my hidden units. Okay? The question, we're going to simplify this. Can we, using the same formulation as we have with TAGI, learn one segment using only two data points? Okay, but now we're going to pass this segment through an activation function. Okay, so we're going to explore this limitation of inference through a one hidden unit neural net. So we have our single input x, we have one hidden unit that's going to be passed through a ReLU activation function, and we have one z output. Okay, so we can formulate this as z output is w(a1) plus b, where a1 is a ReLU of z1, and z1 is w0x plus b0. Okay, this is simple MLP, but just with one hidden unit. So in this case, if we want to write it as a one sequence equation, so we're going to have e z1, which is w0x plus b0. All of this in ReLU, this is a1, times w1 plus b1. This is going to be my z output. And in this case, all my four parameters, w0, w1, b0, b1, are going to be Gaussian random variables. Okay, so I made a little interactive example to see how it works. Okay, I have my four parameters. Mu for my bias 1, for my weight 1, b0, and w0. So my two bias, so the last bias, the first bias, last weight, first weight, and these are the standard deviation. Can you tell me what's going to happen if I move the bias? So if I just redraw here so that you can remember, x, I'm really bad. Let's do it properly. So we have x, we have z, and we have z output. Okay? So this is b1, this is w1, this is b0, w0. Okay? What happens if I play with b1? The bias that goes here. So BA1 is my first slider. So I should explain this. The axes are all the same. It's x from -1 to 1. Okay? The vertical axis here is z. Okay? Z is my first variable here. Then I pass z through ReLU. This is the result. If I multiply the output ReLU times my weight here, this is WA. WA plus B gives me z output. Okay?
Up and down, right?
Is going to move up and down. So if we move mu1, I'm going to move the output up and down. Okay, good. What is going to happen if I play with the uncertainty of b1? if I increase uncertainty of B1.
It affects the uncertainty.
So it's gonna uniformly change the uncertainty around my function. Okay, perfect. Then what happens if I play with W1?
Slope.
Slope of what?
The last graph, the top graph.
So the top, what about this one as well? Because it's W times A, we're gonna affect the slope of this one.
You said W1.
Yeah, W1, but this is W1 times A.
Oh, okay.
Okay, so this is W1
Yes.
times A. The little difference in this and B is the bias. So it's gonna affect the slope. And this is passed in ReLU, so it's only gonna affect the slope on this side. Okay? So if we're right, so this plays with the slope. If I bring it negative, it's gonna bring the slope on the other side. Okay? What if I change the uncertainty on this guy?
And through GME, right? The uncertainty on the right side of those two upper graphs.
It's the uncertainty on the W. So it's the uncertainty, yeah, on this, only this one. So am I gonna have, like before, uncertainty uniform across the domain?
Not uniform, just the right side, right?
Just the right side? Is it gonna be uniform on the right side? Would be weird. What happened at 0? It's gonna be linear. Okay? So if I increase this one, you see I have kind of the tapering effect. Okay? Okay, this is for W. Now, these were the easy ones. Okay? With the harder one. What happened if I move that B0? Okay? Before getting into the ReLU. So it's like,
The slope will be affected.
which slope?
Well, the effect when it gets cut off, no?
Yeah.
Can you expand on this?
Because you're moving the other value up and down, and that domain
So
changes
it's like-
basically.
It's
Like
this Z is W0x plus B. So if I change B, it's gonna move up and down this curve. Okay, because the B1 was moving around all this, B0 is moving around all this. Okay, so then what's gonna be the impact of moving around this?
that's what gets passed to ReLU.
So that's when it gets past the ReLU. So it's gonna move left and right, this inflection point. Okay, so if we increase it, it's gonna move to the left. Because you see that the curve here moves, and if we move it to the right, so it's gonna move it to the left. Okay, this is what happened because of the truncation of the ReLU. What's gonna happen if we change the uncertainty on that B? What happens if we bring it to 0?
It's going to be flat because everything is 0. If actually no, the bias is there.
So if we put it to 0, all the uncertainty about, you see that here, it's not ReLU, it's kind of smooth. It's gonna make it really sharp. Because we don't have any uncertainty about the position of that inflection point. If on the opposite we make it really large, it makes it really smooth. Okay? And again, when I'm presenting all of this, I'm not judging you. I just have one step ahead of you. I had the same uncertainty before running on these experiments. Okay? I'm not saying this, you're no good, you don't know the answer. I didn't know the answer either. That's why I did this. To really understand what's going on. Okay?
But trying to answer usually helps remember as well.
Yeah. And that's why I also asked you the question, so that you can do the exercise on a fast forward process. But you see that the more uncertainty we have, the more uncertainty we have about the position of that inflection point, and that reflects on the whole thing. Okay? Last parameter, the W0. What's going to be the effect on my last figure here?
Slope.
It's going to change the slope. Okay? What's going to be the effect of a change of slope here? What is going to be the effect there of a change of slope? What's going to be the effect on my left-hand side?
We remove the turning points.
Nothing's going to be changed on the left side because the slope is about 0, right?
The slope everything that's on the left side is not going to be affected. Okay, we're only going to affect the slope here. Okay, what about here? Same thing, same thing. Okay, this is if we change the slope in the positive range. What if I bring the slope in the negative range?
By making it negative?
Because I can go from +1 to -1. What if I bring my slope to -1? Because now the slope is +1.
We mirror the whole thing.
Like
there.
this.
I'm going to mirror the whole thing. So the ReLU is going to be flipped. Okay? So if I change and I reduce the slope, it's going to affect my slope on the right-hand side. But if I flip it, it kind of flipped my ReLU. So ReLU is kind of the other way around. Okay, so I can mirror where I put my domain to 0 and where do I activate it. Okay? And same thing, if we change the uncertainty on this one, it's going to have the same effect a bit like changing the variance on the weight on top. Okay, so it gives a little more insight about what's going on about those 4 parameters. Okay? So let's reuse it now to see what happened. I'm going to do in the first case a very simple one. Okay? Technically I have 4 parameters, but I'm going to fix 2. I'm going to assume that W0 and B0 are constant. Okay? So my equation is going to be W0 is going to be -1 and B0 is going to be 0. Okay? And I'm only going to learn W1 and B1. So it's like if my activation function, the output would be deterministic. Okay? So I only have everything at a 0 here because it's deterministic. I have this uncertainty here, and this is my prior on Z output. Okay? I have a first point. Second point, I already have learned anything that there is to learn. And third point. Okay? I myself created that example because I knew that if I had these 3 points, I should be able to model it exactly. And indeed, with those 3 points, I can exactly capture this. But this is not fair because that assumes that I knew exactly where to position that point to leave exactly just that part free. Okay? And in this case, this is equivalent to linear regression. That's why it works so well. There's no uncertainty there. I position everything exactly. I just need to find the bias and the slopes, and everything is defined correctly. This is like, since this remains deterministic, this is the same thing as just having a deterministic constant there. Okay? What if instead, because if I would have flipped the result, okay, and now I put the exact 3 points, but flip the other way around, it's not going to work anymore. Okay, I have a first point, second point, third point. The same point that I flipped with respect to a vertical axis, it doesn't learn the correct relationship anymore. Okay, because it would have required a prior knowledge of exactly where should I position which part of my activation function for it to work. And with that -1, it would give me that part that is flexible, I can do it. So now the solution to this could be to put a broad prior on my 4 parameters, to not necessarily assume that W0 will make my left branch or right branch move. Okay, so I'm going to assume that they all have 0 mean. They can take either way, -1 and +1, and a very large standard deviation, which is going to put a really broad prior on everything. So now you see that on A, I have no very strict prior. Okay, so it can go either way, and it makes a really broad prior on my Z output. Now I have those 3 points. Okay, after epoch 1, this is what it learns. Not much. Okay, epoch 2, 3, 4, 5. Okay, we need several epochs, but starting from a broad prior, it can go there. Okay, but it requires several epochs. And here, keep in mind, I consider a full covariance. If I would consider a diagonal covariance, I would not perform as well. Okay, I would get the same behavior, but we need more epoch to do so. Okay. Now, can we do better by having a kind of targeted prior? I don't want to make it -1 and 0 as before, but I don't want to make it fully broad neither because this requires way too many epochs. I'm going to say my W0 and B0, theoretically I know it would require -1 and 0. Okay, but now I'm going to put some more uncertainty around it. I'm not going to put them as certain. Would it work? So we can see that here, this is my prior. Okay, right now disregard this. Or don't disregard this. This is the covariance between all of my parameters. So W0, B0 are the blue that you don't see and orange, W1, B1, green, and red. And what you can see is that with respect to each of those values, the mean value of those parameters, the covariance between the output and those parameters, it's all linear, it's all constant. Okay, this is just my prior, right now that I don't know anything. I'm gonna see the first same tree observation. I'm gonna see, can I learn? After one epoch, it can learn. Okay, because I have more targeted, more narrow prior. But look at what happened here. The covariance for the blue one and the orange one, the W0, B0, is not constant anymore with respect to the parameter, the mean value of the parameter. What does it mean? And the W1 and U1 are constant. Okay, we have a linear relationship with respect to the output for these two parameters. And that means that the covariance for any value of the prior I could have here is always the same, always have the same covariance. So we're always going to learn the same thing no matter where we start. But this is not true for W0 and B0. If I start in one region of the domain, I'm going to learn something. If I start in another region of the domain, I'm going to learn something else. Okay, so for W0, I start at -1. For B0, I start at 0. Okay, but if I flip those, I'm not going to learn. Because I'm not going to start in the right region of my prior. Okay, so whenever we have such nonlinear relationship as introduced by the activation function, or covariance between the parameters and the parameters and the output is going to depend on the mean value. Okay, so our capacity to learn exactly will depend upon our capacity to correctly initially specify our prior. But the goal of a neural net is to not specify the prior, to be able to generalize because we don't know what is the function. Okay, so this is problematic. So if the conclusion we can look from this one hidden unit experiment is that it's only possible to learn in one epoch if our prior is correctly specified for our parameters. So in that case, if the covariance is in the right region of the domain, it will lead us to where we want to go. And in general, considering a diagonal covariance will degrade our capacity to learn quickly. Okay, so now this is the experiment we deal in a kind of simplified fashion. Can we learn with a one hidden unit this segment? Now, what if we use instead two hidden units? Could we learn these two segments using 4 data points? Okay, would that be easier? So now I'm going to have 2 hidden units. Okay, so 2 hidden units, so 2 weight, 2 bias, 2 weights, 1 bias here. Okay, and now to start, I'm going to say both the bias here for my Z layer, hidden layer are 0, and my weights here, one weight is -1, the other one is +1. So the -1 is the blue, the +1 is the yellow. Okay, so I'm going to be able to capture both branches. So even if I have a point on the left, one branch is going to capture it. If I have some point on the right, the other branches should capture it. So I shouldn't need to specify where my prior is defined. Because now I have 2 hidden units, one active, the other one not active. Okay? So this is if we sum them up, and this is my general prior. Okay? So I have the same 3 points as usual. Oh no, I have a different set of points, now I have 4 points. Okay? So first point, okay. Second point, so we see that one of the branch got activated and learned something that is fairly good in one epoch, or at least with 2 points, this branch captured a very precise model of what's going on. Okay, what if we have 2 more points? 1, 2. Not too bad. Okay, not too bad. So now we're going to do the same thing. Another example of 4 points. So 1, 2, okay, again, so the relation is reversed. It's still working the other way around. 3, 4. Okay, not as good, but not too bad either. Okay? So if I have 2 branches and each branch is kind of independent, I kind of can get my way around it. Okay? If we do a second epoch, it's going to get way more precise. Okay? So if we can disentangle our domains, we can pull it away. And it's way better than just assuming a broad prior. Because broad prior will need to be dragged around to get in that right region of the domain. Instead of having two activation units that are kind of back to back, where one is active, the other one is not. One is active, the other one is not. Okay, they're kind of mutually exclusive. What if they are working like this? In this part of the domain, none is active. In this part of the domain, only this is active. In this part of the domain, both are active. Okay? In that case, I assume this structure by assuming the first bias. We said that the bias on the first layer was moving around or activation function here. So by having 0.6, it moved this one to the left, and both have a weight of +1. Okay? So in that case, I have a first observation, a second observation, third observation, fourth observation. Okay? Not too bad. If I do a second epoch, okay, it kind of adapts to the domain, and you can see that in this case, it really finds that it's not only hidden unit 1 or hidden unit 2 that learns a relationship. It learned what superposition of those two hidden units really describe the relationship that I can see here. Okay, so through superposition, either by being back to back or by interacting with each other, they can do a decent job. They don't do it in one epoch, but it's better than just assuming a broad prior. Okay? So the conclusion for this two hidden unit experiment is that it's not possible to learn with one epoch. Okay? Overlaying multiple hidden units allow to prevent having to use a broad prior. But now the issue is that if we overlay multiple hidden units or their effect on top of each other, some of the parameters are going to affect all possible response of Z. Okay, now if I modify the bias of the variance of one hidden unit, all the domain of Z is modified. Because we need interaction between all hidden units together to make the correct response. So it's not going to be possible to modify one part of the domain while affecting all the other parts of the domain, because they're all intertwined together now if we do this. And this is what we have everywhere in neural nets. And again, as a side note, considering diagonal covariance structure will degrade the learning. Now the last thing we're going to look at is what if we extend this to 3 hidden units? Okay, so now we have the same problem as before, 3 hidden units. I specified a prior to have all of them kind of all separated. And we're going to try to see epoch 1. There's the same set of 4 data points. Epoch 1, not so bad. 2, okay, a little better. And we see that it's an interaction between the 3, but it's mostly 2 of them that captured. The other one is just kind of a redundant variable. Okay, we have again that kind of redundancy, not identifiability. It kind of can handle it. Okay, but still cannot necessarily do it in one epoch. And in practice, this is what we have on a much larger scale in a neural net. Okay, this is an example in 1D, but this is the same thing that happened in a million dimension. Only you can see instead of being a line, there's going to be planes and hyperplanes. Okay. So the conclusion from this, still not possible to learn from one epoch. Same thing, overlying multiple hidden units allow preventing the use of a broad prior. And the learning performance will depend on the initial biases. Okay, depending on where I put these initial curve, some of this position works really well, some of those positions don't work well at all. Okay, I need to put these inflection points in the curve around the point where I want transition between my segments. Okay, if the initial points are not well located, it's not going to work as well as I have shown in this example. And the main issue is that, again, some parameters for each of the hidden units have effect everywhere across the domain of my function. So I modify one, I need to modify all of my other hidden units as well. I cannot modify only one hidden unit at a time. They must all be modified simultaneously, because now many of them are active simultaneously in the same part of the domain. And considering a diagonal covariance structure will degrade the learning speed. So the overall conclusion from the experiments I presented today is first, learning from one epoch at scale in real neural network seems infeasible. Okay, given that we can barely do it on a linear regression problem, makes me think that with the current neural net architecture, learning in one epoch is simply infeasible. Okay, and the root cause of this seems to originate from 2 things. First, the nonlinearity in activation function will make our covariance between the parameters prior to that nonlinearity and the output being function of the mean of our parameters. If we correctly initialize that parameter, we're going to learn really quick. If we don't, we're going to need to drag over multiple epochs of parameter until it comes in the right region of the domain. That forces it to, in practice, since we initialize randomly, to be doomed to have wrongly initialized parameters. And the second issue is that we have multiple overlaid hidden units, making that if we modify one of the parameters, we need to modify the parameters of all of our other activation functions, or at least all of those are active in that same domain. Again, that's problematic if we want to do sequential processing and if we want to do, for instance, continual learning. So what are the possible solutions? So one could be to maybe consider a hierarchical approach for the uncertainty that leads to that covariance. To consider the fact that we don't know exactly the position of our prior parameter, such that that covariance is not something deterministic. The covariance would itself be a random variable. Maybe that could improve. That's a maybe. Okay, I don't put a high likelihood of success. It would be worth investigating, but I'm not sure to what extent we can do this in a closed form solution. The second way would be to come up with a completely new learning paradigm that will disentangle the effect of each hidden unit. Okay, the goal will be so that each hidden unit create a local model of a single neighborhood, where each of those neighborhoods would be decoupled from the other. So they will all be kind of small linear regression problems, very locally. But we saw that we can do a really good job with that simple problem. Can we, instead of making one big entangled problem, make tons of tiny pieces problem, which we saw that we can have a really good performance learning in one epoch on those small problems. So what could be a way to do this, and I'm going to conclude on this. Imagine that I have my same function, x cubed. Okay, I have those 2 points. So what I could do, from what I saw earlier with linear regression, I can in one epoch learn a local model for that thing. But then what happens? If I have other points, that model is rubbish for predicting those points. So I need to learn in what range is that model valid. So I need to assign a probability density associated with what is the probability density of the coordinates, the covariates for which this model is valid. Okay, this is represented by the PDF here, which represents the probability density of the points that are valid for that model. Okay, then I can do the same thing for my other part of the domain. Then each of those would be parameterized by, say, a slope and a bias, so a weight and a bias. And I have a set, these are thetas, and we have eta, where etas are going to be my location parameter, representing the span of validity of each of those models that are independent from each other. But then, what if I try to predict the last compilation I did, I think I didn't do it correctly. Anyway, okay, I missed some slide, but if we want to apply this in the learning phase, okay? I'm not sure what's going to happen here next, but the sequence is not right. So in the learning phase, what we're going to say is that y equals wx plus bi plus v. Okay, where I represent the ith of our model. Okay? So in this case, what is I? Is the index, which is the argument that maximizes this. What is for each of our local neighborhood? The probability that this neighborhood predict the training data at hand. So what about this point? What is the probability that this point is predicted by this neighborhood? But not just only the location or the span and the predicted response. Okay, so like this, I can really isolate and learn only one neighborhood at a time. The one that is best at predicting that input covariant as well as the system response. Okay, so this should appear first. Okay, but then what happens if we try to learn here? I don't have anything there. I don't have any neighborhood. Okay, so when I do this, I always have a default neighborhood. The default neighborhood is the I don't know neighborhood. And that I don't know neighborhood is always put in competition with those that are already learned. Okay, if we try to query here, this one is gonna come up with the highest probability. If we try to query here, this one is gonna get out with higher probability. If we try to query here, neither of those is gonna return a high probability. So it's gonna resort to the I don't know neighborhood. And the neighborhood, whenever you trigger the I don't know neighborhood, it's a sign that you need to create a new neighborhood for the new point you're training. So I'm gonna create a new neighborhood theta 3, which now I've only seen one point. Then what I'm gonna do, and in this case, when we're gonna learn the full posterior, because we can do all this with Gaussian inference at AGBI. We go back on our feet, this is just linear regression. It's just for local neighborhoods. Okay, then I'm gonna have a second point, I'm gonna learn, and this is my current neighborhood. And I can go on like this, and when I've covered enough of my domain, I can query to predict. Okay, so in that case, I want to predict at that location X. But I don't know the Y, I want to predict. So I cannot define my I based on X and Y. I only base it on my, what is the prior probability of predicting X at that location for each neighborhood. Okay, now I don't have to use only one neighborhood. I can make a weighted sum of the prediction from each neighborhood, where Wi is going to be the weighted bias of that specific neighborhood, where it's going to be weighted by the probability. And in this case, if we want to make it probabilistic, we can fully consider a posterior uncertainty about the parameters and the hyperparameters. So this is still work in progress. I've started implementing this. The preliminary result I have are promising, but it's too early. I'm going to try when I'm going to be more advanced to show you some example of how it works. There are multiple challenges. How do we extend this to multiple dimensions? So instead of having linear regression, it's going to be planes. This is going to be, I think, pretty much straightforward, but then how can we leverage this for multi-layered architecture? Not only single layer. We can do the same thing, put multiple layers on top of each other to try to increase the efficiency. Okay, and there are many more challenges, but this is the idea, with the goal in mind to enable online learning in one epoch and continual learning in different ways. That's it. Questions?
Yeah, this is one of the multidimensionality, because it feels to me that whenever you have higher dimensions,
I'm just going to stop the recording.